So first of all, who am I? We had a lovely introduction, but very shortly, I'm a data scientist at Cato Networks. Cato is a cybersecurity company that delivers a SASE platform. SASE stands for Secure Access Service Edge, which is the convergence of networking and security in a single global service. We have a global backbone of POPs, and it's cloud native. I came to Cato Networks after some work as a data scientist in diverse fields, as mentioned, and this talk will be about one of my main interests, which is networks assets discovery. So what is the agenda for this talk? We'll have two main parts, passive fingerprinting and statistical fingerprinting. I'll start with general motivation, focusing on the issues with IoTs and unmanaged devices as a motivator. Then we'll dive into passive fingerprinting. We'll start with some definitions, talk about the setup of fingerprinting system, which protocols can be used, a lot of examples, and we'll summarize with the pros and cons. This will give us the motivation to speak about statistical fingerprinting. I'll introduce the concept of classification confidence, which also will be necessary for our data preparation. And then we'll dive into statistical fingerprinting. So again, we'll discuss some definitions and remind ourselves the structure of MAC addresses, and then focus on the MAC lookup algorithm. Starting with an overview, we'll talk a lot about the preparation of the lookup file, how classification is based on it, summarize with pros and cons, and connect it all together. So we have a lot to talk about. Let's start. So as I mentioned, our motivation is the prevalence of unmanaged devices. We all know that the network is only as secure as its weakest link. The problem is that enterprises today are full with unmanaged devices. By unmanaged devices, I mean both IoTs and bring your own devices. These do not contain some agent and are not tracked by the company. Our solution for this problem is, of course, our hero device fingerprinting, which enables us to manage our inventory, assess risk per device, and apply policies per device type. Let's dive deeper in and focus on IoT security. So why does IoT security matters to us? As mentioned, it has become a very prevalent issue. There are massive numbers of IoT devices. They are spread across sites of companies everywhere around the world, etc. These devices pose some security weakness? Yes, they have weak encryptions and security. They are most of the time aren't patched, etc. Are they commonly exploited? Yes, of course. They're used for breaching companies and creating botnets and causing denial of service. Are these exploits prevalent as well? Yes. Looking at the dark web, there's a thriving market for such hacking tools for IoT devices. So let's get the terminology precise. By passive fingerprinting, I mean the identification of properties of network entities by only passively observing the network traffic. This is as opposed to active fingerprinting, in which we probe the network with crafted packets and analyze the responses. An example for passive fingerprinting would be looking at the user agent and HTTP headers, while crafted packets could be, for example, a TCP SYN packet. The disadvantages that we'll see with these two methods can be somewhat remediated with statistical fingerprinting, which I'm here to sell to you. We can identify properties with statistical or machine learning based methods, which are inferred from large data sets. In this lecture, we'll dive into statistics about MAC addresses and what can be learned from them. So let's continue with passive fingerprinting. An example fingerprint, analogously to the fingerprint of a human being, is some specific collection of conditions which helps us identify a device. In this case, this is a fingerprint for Amazon Echo, the smart speaker controlled by a voice assistant. And we can see that by looking at different OSI model layers, at specific fields, this device can be precisely identified. For example, user agent and HTTP using this regular expression, some TCP option combinations, and the time to live in the IP level. Where does a fingerprinting system sit on the network? Well, this depends on the network. So in simple networks, the modem router has visibility into all of the devices, whether they're connected through Ethernet or wireless communication. So our agent or classifier can just sit on the router. Unfortunately, this isn't usually the case. In Cato, we have about 3,000 customers. They have sites all around the world, connected by the WAN, and each LAN can be divided into subnets. For example, like a Wi-Fi guest subnet, or printers or workstations. So sitting on the router will not be completely, will not give us full visibility. For example, we won't see the MAC addresses of the workstations. This calls for either putting agents on a more sophisticated deployment. So either putting agents on each subnet, or using specific agents on endpoints. When we have successfully deployed such a classifier, we have a plethora of protocols to use for classification. As a general rule of thumb, the higher we go in the OSI model, the more granular our classification can be, but the easier it can be spoofed, and the less reliable it will become. For example, as we saw with the user agent. And now let's dive into a bunch of examples which will show us which classifications can be made at which granularity level. So starting from the bottom up, looking at the MAC address, if you recall, the first half indicates on the organization, the OUI, and looking at this packet capture, I hope you can see it. If not, I can zoom in, but I think it's clear from the signature. We can identify a D-Link device. Obviously not very granular. Continuing to the TCP/IP layer, and specifically looking, for example, at the first packet, the SYN packet in the three-part handshake, we can look at the options which we already saw in the echo, and for example, the time to live at the IP level. This allows us to classify devices such as this Android TV. It's hard to see, but trust me that the time to live is 64, and these options are found there. Continuing to the DHCP protocol, IoT devices, when they connect to a network, they want to get some configurations. For example, what's their IP, what's the gateway IP, the DNS server. So they send DHCP packets, which can contain very useful information. In this case, this pattern can identify for us, looking at the vendor class, the life size icon. This is the option number 60. And looking at option 12, we can even find that the host name contains like a very specific name, in this case, the Lightify. These are smart bulbs. Continuing with the application layer, HTTP is also a very common protocol used for the communication of IoT devices to their servers. This can be for firmware updates, getting like time settings, all kinds of updates. So it's still very common to see IoTs using HTTP over the web. And in this case, just looking at the GET request, we can identify, for example, this motion sensor when it asks for a firmware update. Here we look at the host and the URI, and lo and behold, the host tells us the vendor, basically. The URI contains the specific model. Another example, identifying the Samsung Galaxy based on its user agent. Last but not least, let's look at the DNS protocol. Devices, IoT devices need to resolve domain names, every device, and in their case, they need to know the IP of their vendor server. So they send DNS address requests, which go through our router to the DNS server that is configured for them. They usually have some pre-configured DNS server on them, which very helpful to us, can contain very useful information. So let's look at this Philips Hue bridge. This is a device that talks to smart bulbs, smart light bulbs, and it is connected to the internet. And we can see both the bridge here and the Philips company name. So we saw a lot of protocols, but using these protocols alone won't give us the best result. We should obviously rely on a combination of protocols, and this way we'll have much stronger signatures. So this combination can be thought of in two ways, with two methods. Either looking at single flows or multi-flows, meaning either using a stateless classification or a stateful one. In this case, we see large combinations of conditions, and starting from the bottom up, the MAC tells us, using the OUI vendor, the vendor, Samsung. The TCP IP tells us it's an Android-based operating system, and we can see in the user agent the exact model, revealing it's a Galaxy watch. As for the stateful setup, we can start by figuring out from the TCP packet that this is an Amazon device of an Android OS, and then look, for example, at the DNS to understand it is specifically the Amazon device Fire TV. So wrapping this section up, let's further discuss the pros and cons of passive fingerprinting as a motivation for the next section. Well, obviously it's very simple. Once I configure some signature, it will just work unless something is changed, of course, and it can be very reliable, especially when we combine a lot of protocols and use different indicators. Also, as mentioned, compared to active fingerprinting, it's much less intrusive. We don't fill the network of our customers with packets and watch them. As you can see, there's a much longer list of cons, but we work with what we got. First of all, as we discussed, there's a limited visibility into the subnetworks. In addition, it is not always possible, or not every protocol enables us inspection of its content. Two main key examples are, first of all, the subject of MAC randomization. As you all know, MAC in mobiles is randomized by default. We'll touch about it later. In addition, for example, HTTP secure limits us to perform deep packet inspection. In addition, as we saw, traffic isn't obviously 100% reliable and can be spoofed. Unfortunately, as a rule of thumb, low granularity protocols are the more reliable ones. Another issue is that we have to prepare signatures which are more robust if we want more reliable detection. So it's more work for us. Another issue is the issue of scalability, and this is a big one. Just imagine that you have to prepare a signature for every device ever created in the world. Of course, you can automate some aspects. We have AI to help us today, EA for us, less EA for test asset managers. Final con is that this method is delayed. In particular, when a device connects, or even after it has been connected for a while, we have to wait for a specific packet, and only then, assuming this is the packet required for classification, will we be able to classify that device. These two issues will be remedied in statistical fingerprinting. I want to touch on the subject of classification confidence. Obviously, as we saw, some signatures vary in our confidence regarding them. I won't get into formulas here, but again, rules of thumbs for how to calculate this confidence. First of all, we will use a combination of different classification indicators. So by indicator, just to make clear, I mean stuff like the user agent or the DHCP vendor class. We will need to assign different weights per indicator. Strong ones will be given higher weights. Of course, it's kind of an art. DHCP vendor class, as mentioned, is a strong one. Indicators that come from clients on devices are obviously given higher priority. In general, we will be giving higher confidence when multiple indicators classify a device with the same class, and more important than that there are no clashes between the classifications, no contradictions. If there are contradictions, we can obviously use some majority vote and set some threshold, like, for example, we will only finalize this classification if over 95% of the devices, of the indicators give the same classification. Another reason to raise the confidence is that a single indicator has repeatedly classified, given the same classification. You will agree with me, it is very strange if, based on the user agent, we keep seeing different devices. Similarly, we would like to see the same classifications over multiple attempts with, for example, complex signatures. Why is it so important to us in the context of statistical fingerprinting? It's obviously very important to begin with, because we can use these confident classifications as our labeled data. We have to set some threshold, and classifications that are, we're I won't say 99% confident, but you get the idea, can be used as data we can perform statistics on. So this brings us to statistical fingerprinting. We will define it, it's a very general definition, data-driven creation of signatures. But what does it actually mean? Basically, the creation of signatures using data can be put in simple terms of 3 steps. First of all, we have to collect our data set, which contains some features of some network entity. Based on this data set, we will create rules which are generalized about unseen feature values. Our feature, as I mentioned, would be the MAC address. So we will literally try to predict device classifications for devices with unpreviously seen MACs. The last step is to infer this classification and also calculate some confidence score. So a quick reminder about MAC addresses. They are built out of 12 hexas, the uniquely identified network interface cards, and they are assigned to them by IEEE, the Institute of Electrical and Electronics Engineers. The first half uniquely identifies the organization, and this is publicly available and published. And the second half is basically just a random or less random serial number. It is very important for our cause. It basically makes it possible to begin with, to understand that manufacturers buy bulk MACs, and these MACs are sequential. So like Samsung can buy, I don't know, thousands, 10,000s MACs with sequential orders. And as I mentioned, although the second half of the address doesn't hold any meaning, it is very crucial for us. So I have given you some hints, and we have to take a few seconds to think about any idea for how would you use this to classify a new device which you have not seen its MAC before. So I trust that everyone has figured the entire algorithm, but just for fun, let's go over it. Oh, I'm sorry. Just one note about MAC randomization. Basically, there is an issue with the uniqueness of MACs. It can violate privacy. especially for example, a mobile device that travels around the world. We can geolocate it. The way to protect user privacy is by randomizing the MAC. This is done by default in mobile devices when they connect to networks. The randomization ruins our plans. We can't use this for statistical fingerprinting, but it is very easily detected, and we just exclude it from our data set. The second hexadecimal gives it away. And although this looks like a big issue, and fingerprinting is limited for mobiles, it is still very practical for static devices. So let's now see these three steps we have defined before, applied to the algorithm of MAC lookup. So step number one, we need to collect data. Data in this case is based on passively classified devices. For our cause, let's assume we have, as we do have in Cato, some engine or collection of systems which gives us classifications and their confidence. We will use this format for data. We will have the MAC address on the first column, then a few layers of device classification hierarchy. I'll touch on it in a second. And finally, the passive confidence. Important to differentiate it from the statistical confidence, which is calculated differently. We'll touch on that as well. The next step is creating some generalizing rules. In our case, we create a lookup table. It can be as simple as a CSV file. This file will be created periodically. We do it every week based on our collected passively classified data, while the passively classified data will be our source separate file, and it will only keep on renewing every some period. So just to clarify, our lookup table will keep on growing forever, while our passively classified devices file is something that has some retention rate, because new devices are classified for some period of time, and we don't keep every device of every customer, etc. The lookup file will be used for lookup, for a search. We will base it on the first few hexadecimals of the MAC. I will call this sub-MAC. As you can see on the left column, we use a sub-MAC length, for example, of 11 hexas, ending with 6 and 7. And then we use a sub-MAC length of 10, the one ending with 5F. And each of these rows indicates a different classification with a different confidence for a different value of the sub-MAC. The third steps is that when given a new address, we calculate its classification by searching this file. So in this example, when given something that ends with 60, obviously we would all guess that the correct classification is the first row. How do we prepare this file? So as mentioned before, we have to collect a large data set. The data set contains classifications with different hierarchies. In Cato, we use the class, for example, laptop, the product, for example, MacBook, and the model like Pro or Air. This will be our running example. We then create a submac table, which is based on just taking the original data and removing the required number of hexes from the end. Notice that the more hexes we removed, the more predictions are possible based on this row. The more devices we will have, the more submax lengths we could use. We then prune. We will see a lot of pruning here, and by prune I just mean delete. Submax that don't have enough devices, enough classifications for a specific submac length and value. We don't want to keep unneeded stuff that is covered by other rows in the table. And in this first pruning, we require at least 2 out of the 16 devices for the submac length 11, and 25 devices at least for the submac length of 10. So this gives us in the following table. Well, actually, we don't prune anything in the following table. We then explode, meaning add rows to the table. This is done for every layer per specific classification. So, for example, the first row, marked with bold, has 3 layers. This turns into 3 rows after the exploding. Excuse me. The second row, marked with italics, turns into 2 rows. We then group these rows by unique submax and classification. So classifications are per layer. And we can perform some aggregation. In this case, the goal of this is to be able to calculate the proportion of devices. So let me go on this carefully. We can see that there are 3 unique classifications per layer: laptop MacBook Pro, laptop MacBook, which will create the second row, and laptop only. Looking at the the column of exploded classifications per specific submac and layer. For the first row, there is only 1 corresponding row in the initial table. And for the second and third row, there are 2 corresponding rows after the grouping. We also add a row of the number of passive classifications for this specific submac. So this is based basically on the original data. And in this case, we have exactly 2 rows for these submacs. The proportion is then the division between the exploded classifications and the passive classification. So 1/2 gives us a half, 2/2 gives us 1. We prune again. This time we remove rows that have too low a proportion. So for example, if our threshold for pruning is 0.6, we will remove the first row. We then prune yet again. This time we wish to keep only a single result for each submac value. So if there are 2 rows with the same proportion, we just remove the lower layers, which is just less granular. In this example, you see laptop MacBook and laptop. So we will remove the second row of only laptop. There are, of course, cases where there are different proportions. In this case, we will keep the row with the most granular classification only if the proportion is above some threshold, say 0.8. Of course, we have to repeat all of this process for all of the submac lengths. we got something for our length 11 example. So say we get something else for our length 10 submec. We then perform a step which we call neighboring. Basically means filling out rows between the known rows. We'll do this only for the shortest submec length, the length 10 submec, and we fill these intermediate rows with the most granular shared classification. So the example will make it much clearer. We have for submec length 10 these two bolded max, ending with 5.5 and 5.8. And we just fill in the gap of 5.6 and 5.7. We fill it with the lowest shared layer, in this case the product layer, so the classification is laptop MacBook without Pro. Now we concatenate all of the submec length tables. We place the longer submecs on top to sort them first. They can contain more granular classifications, or it is much more likely that we will have enough devices for that. So we just put the length 11 before the 10, and we prune again. We like pruning. I swear this is the last time, I think. In this case, we remove longer submecs in case they are covered by shorter submecs, meaning that the shorter submec can classify the same thing when we look at the same classification. So let's look again at an example. In this case, in the first case, we delete the submec 11. And in the second case, because there are different classifications, there's the Pro there, we keep both of them. Now, how do we classify? We literally just search and find the first row that matches the prefix of the new Mac. So if our final table is as seen in this example, and we're given something that ends with 6 something, we will take the first row. This is the first match. In addition, we will calculate the confidence similarly to the case of the statistical fingerprinting, but based on different heuristics. So what would raise our confidence? It's written, but don't look. Think about it for a second. First of all, the submec length. Obviously, the longer it is, the Mac by which we have made the match, the more confident we are. Second is the proportion. When more devices were used to create this classification, we are more confident. And another point is, did we classify using a neighbor? If we did, we should lower our confidence. This is only relevant, of course, for the shortest submec. A couple more points about the classification. So first of all, we have to integrate both engines of passive and statistical classifications together based on the confidences. I won't go into this too much, but I'll just mention that if there is the same confidence, we will rely on the statistical fingerprint in case the classifications are different. How does this? How well does this work? So in Keto, about 6% of all of our discovered devices originate from statistical fingerprinting. And here I include mobile devices, and I also take into account that other classification engines can override these conclusions. How do we improve upon this algorithm? Well, basically we need more data, something that every data scientist will tell you in every conversation somehow. They'll always get to that. The more fingerprinted devices we have, statistically fingerprinted, the more confidence we'll have, etc., etc., and we could add even shorter submech lengths, submech 9, etc. One small note, this is not a very efficient search, so turn your CSV into a dictionary. What are the pros and cons? So first of all, we saw that this helps us increase coverage in cases that are harder for passive fingerprinting. Second of all, we saw how the scalability issue is solved. We can just run this algorithm. We don't have to do anything. There's an airflow DAG that runs periodically, and the system keeps improving. It isn't delayed. The moment I get some Mac, I don't have to look for any other packets. I can just run the lookup classification. We can use a single feature, and it is not intrusive as active fingerprinting. Of course, there is the one main con, which is also just a requirement. We need a sufficiently large and sufficiently representative data set of confidently classified devices. So summarizing, we saw the challenge in IoT asset management. We understood that it is very crucial for security. We discussed and saw many examples of passive fingerprinting, saw how simple yet reliable it can be. In addition, if you want good fingerprints, use multiple protocols. We then discussed statistical fingerprinting, which can join forces with passive fingerprinting and overcome some of its cons. As mentioned a moment ago, of course, we need enough data and reliable data. But given that data, we have a long list of pros that make it worthwhile. Thank you.